Welcome to Unit 1, Lesson 1, Inverse Trigonometric Functions. Before we start the trig part of this lesson, let's remind ourselves what an inverse function is. So we have three nice, wonderful polynomial functions, warm and dear to our hearts. And if we were to graph these from the basic way, we might make a table of values for each of them. And to find their inverses, we would switch their x and y coordinates. And then notice that the graphs would reflect over the line y equals x. So if I want you to find the inverse of each of these functions algebraically, we are going to replace the y with the x and the x with y. And then you want to solve for y. So please pause this and take the next 90 seconds to find the inverses of each of these functions. All right, so the inverse function of number 1 is the cube root of x plus 5. For number 2, it is x plus 6 over 4, which could be represented as 1/4 x or x over 4 plus 3/2. And notice the inverses to 1 and 2 are functions. On number 3, you can algebraically find an inverse, but you end up with plus or minus root x minus 5 equals y. So for each input, there's going to be more than one output. Therefore, the inverse is not a function. So kind of keep that in mind as we go through inverses of trig functions. When we discuss, do all functions have inverses? They all have an inverse relation, but are they functions? Is any function its own inverse? What's the definition of an inverse function, and can we define inverses for all the trig functions? So let's first talk about the sine curve, our friend the sine curve. All right, so if I make a vertical line, the sine curve passes the vertical line test. That means the sine of x is a function. However, in order for it to be 1-to-1, it would also have to pass the horizontal line test, and it fails miserably because the end behavior of the sine curve goes out to negative infinity and infinity, and the horizontal line is going to be touching in multiple areas. So what's the function here? We have to restrict the domain of the sine curve to the interval negative pi over 2 to pi over 2. We chop off almost the entire sine curve except the piece that starts here at pi over 2 and ends up here at positive pi over 2. Why do we pick this interval? Well, it's where the sine is increasing, it's where the function takes on the full range of values from negative 1 to 1, and it's where the sine is now 1-to-1. So it's still a function, so it passes the vertical line test. But now, if we only look at that yellow portion that I've highlighted, it is now passing the horizontal line test. It's now 1-to-1, therefore the inverse is a function. So the restricted domain from negative pi over 2 to pi over 2 for y equals sine of x has a unique inverse function called the inverse sine function. We can denote that as the arc sine of x, or we can talk about it as the inverse sine of x. So this area right here, that's not an exponent or a reciprocal, it's the inverse sine. So from the Public Service Department, as a reminder, the inverse sine does not mean 1 over the sine of x. It means the cosecant of x, so make sure you keep that straight for your understanding as you move forward, as well as for calculator work. So the main concept is that inverses of trigonometric functions find angles. So let's do a few problems. If I look at the arc sine of root 2 over 2, notice that we are inputting a value. This is a value. And by finding the arc sine or the inverse sine, it's going to yield an angle. So specifically, when I have the arc sine of root 2 over 2, because it is an arc sine, I am looking for a y value either on my unit circle or on the y equals sine x graph that is root 2 over 2, but the domain is between negative pi over 2 and pi over 2. So I am only looking on this piece of the unit circle or only on this piece of the graph. So I found a y coordinate that is root 2 over 2 right here at the 45-degree angle location. In radians, it's at pi over 4. Using kind of that same logic, I have a y value here of negative root 3 over 2, and I have to find the inverse sine. So the domain is between negative pi over 2 and pi over 2, and this is where I see negative root 3 over 2. Now you need to be careful. I'm not going to use the counterclockwise angle of 300 degrees because that's not in the domain. The domain has to be between negative pi over 2 and pi over 2, or negative 90 to 90. 300 on a number line is not in between negative 90 and 90. So what you need to use is the clockwise direction, or the negative angle. So the negative angle would be negative pi over 3 or negative 60 degrees. Now when you're being asked to find the arc sine of negative 2, again, you're inputting a y value. And if I hunt and peck on the unit circle, I'm not seeing any negative 2 as a y value. If I look at the graph, we don't have any outputs on the sine curve that are negative 2. Negative 2 is not in the domain. If you think about your domain in radian form and you just approximate pi to be 3, again, that's not exact, but just approximate, then basically in radians, you're looking at values between negative 1.5 approximately to 1.5. So negative 2 falls outside that range, and therefore this is an undefined angle. There is no angle that's going to yield an output of negative 2. So it follows, the same pattern holds true for inverse, cosine, and tangent. Cosine and tangent are functions. However, they are not one-to-one. They fail the horizontal line test. So we restrict the domain so that the inverse is a function. So here are some formal definitions. Here's the definition of the inverse sine function. The inverse sine function is defined as y equals arc sine of x if and only if, notice, we switch the x and the y. So with regular sine of x, so with the regular sine curve, not the inverse, we might input angles. They become the range of the inverse. On the regular sine curve, we output values. They become the domain of the inverse. So the domain is going to yield values from negative 1 to 1. And the range is going to yield values from negative pi over 2 to negative pi over 2. In unit circle language, that means we are looking for angles in the first and the fourth quadrant. We have a almost similar conversation with cosine, except that we talk about a different piece of the cosine curve. We can't go from negative pi over 2 to pi over 2 because if we did, this piece of the graph is not one-to-one. So we look at the places from 0 to pi. So again, the inverse cosine function is defined by y equals arc cosine of x if and only if the cosine of y is equal to x. So we switch the x and the y. So my angle values become the range of the inverse cosine, and my value ranges become the domain of the cosine. So your domain of the inverse is between negative 1 to 1, and your range is from 0 to pi. So in unit circle language, that means we are looking in the first and second quadrants for inverse angles of the cosine. And last but not least with the tangent. With tangent, okay, the function is defined. Again, we're switching our x and y. Now, I just picked from negative pi over 2 to pi over 2. Obviously, I could have kept going. And the range, or excuse me, the domain of the tangent becomes the range of the inverse. Now, see if this makes sense. Because you have asymptotes, the end behavior of the sine
tangent curve
goes forever and ever up to positive infinity and down forever to negative infinity. So the range is all real numbers. It's a little bit different than the sine and the cosine. That means that the domain of your inverse is also real numbers. So the domain of the inverse tangent is all real numbers, but you have a range restriction similar to inverse sine of negative pi over 2 to pi over 2. So this applies to quadrants 1 and 4. So let's try a few examples. If I wanted to find the arc cosine of negative root 2 over 2, here's my thought process. First of all, this is an arc cosine. So that means this right here is an x value, and I want to output an angle. So arc cosine is defined in the first and the second quadrants, and I have to find an x value that is negative root 2 over 2. That occurs at 135 degrees or at 3 pi over 4. Again, with inverse cosine of -1, I am given an x value of -1, and I have to find an x value only defined in the first and second quadrants, so I find it here. And so the angle measurement output is going to be pi or 180. Now, when you have arctangent or inverse tangent, you do have to use your noggin a little bit. You have to find a y-coordinate over an x-coordinate that yields 0. So it's not going to be in any of these coordinates that contain 1/2 and √3s over 2. But because it's arctangent, I can only look in the first and the fourth quadrants. So if I would focus on 90 degrees, that would be 1 over 0, which is undefined. And at -90 degrees, that's -1 over 0, also undefined. So the big winner is right here at 0 degrees, 0 radians, because 0 over 1 is 0. And lastly, if I want to find the inverse tangent of -1, I have to find a y over an x coordinate that yields -1. So down here does not yield -1, that's undefined. This is 0, and this is also undefined. So by looking in the first and the fourth quadrants, those are not going to be my areas. In order to get 1, I need the same number in the numerator as the denominator, and since it's a -1, this is where life is good. If I have -√2 over 2 all over positive √2 over 2, this is going to yield 1. And therefore, and remember, I have to use the negative angle because my range values have to be between -pi over 2 and pi over 2. So -pi over 4 and -45 degrees would be the answer to that problem. So if you have listened to this and understand, you have a very short assignment that you should be able to get done in class tomorrow, page 316, numbers 1 to 23 out and 27. And I look forward